coming 7.2 diagonalization. So what we are doing that we're making matrix as diagonal matrix. Then what is the diagonal matrix? So creating diagonal matrix. So it's like a word diagonal. So if we say that 3 by 3, so some number, rest is 0. That is a diagonal matrix. Okay. Why we need this one? We want to make the product of the matrix. For instance, if we have D equal to 2, 0, 0, 3, which is 2 by 2 diagonal matrix, right? So if we want to make a D squared, then there will be 2, 0, 0, 3 and 2, 0, 0, 3, right? Which is the same as 2 squared, 0, 0, 3 squared. Okay, now we want to make a cube. So there is 2, 0, 0, 3 and 2, 0, 0, 3 and 2, 0, 0, 3. So there will be 2 cube. Zero, 0, 3 cube, right? Okay, now we can do more, right? So any power of that will be 2 to the k power 0, 0, 3 to the k power, right? And k must be greater or equal to 10. 10 it's 1. Okay, now look, we say that let us do this one first. Let a equal to 7 to negative 4, 1. And find a to the k, given that a equal to p the inverse of p. So where p is the matrix 1, 1, negative 1, negative 2, d, which is diagonal matrix. So we have 2, 0, 0, 3, which is we had earlier, right? Start with that. Okay, now how do you find the inverse of p? So we have 1 over determinant of p and adjugate or adjoint matrix, right? So 2 by 2. So determinant of p is easy, right? Straightforward. So we multiply this way. So negative 2 plus 1, right? So which is negative 1. Adjoint of p, 2 by 2. So we had A, B, C, D. So we switch over DNA. Then we give it to the A, B, C, right? That's adjoint. So we will get P, which is negative 2, 1, switch over diagonally, and then give it to the negative sign here. Okay, so we get inverse over P, so which is negative 1, and there will be negative 2, negative 1, 1, 1. There will be positive 2, positive 1, negative 1, negative 1, right? Okay. Thank you very much. All right, so we have a squared So a squared, which is, we are going to use this one, P, the product of matrix P and diagonal, and the inverse of matrix P, right? So we have P, the inverse of that, P, the inverse of that, right? Okay. Then we can say that there will be identity, right? So we will have, so there will be P D squared inverse of D, right? Okay, then there will be matrix P, which is that, and D squared, which is 2 squared and 3 squared there. And 2 squared, 0, 3 squared, right? And inverse of P, which is just right there. So let us do this. Copy. Okay, now A cube. So let us do, we have a P. So basically A squared times A, right? That is P D squared inverse of that. And we get A, which is P diagonal matrix, then inverse of P, right? Okay, so there will be P D squared. We have inverse of P and P D inverse of P. So there will be identity again. And we get D, matrix D and inverse of P. So we get P D cube inverse of P, right? Okay. Now, then we can see the pattern. Let me rewrite it as this one. So everything is the same. We are changing only 2 cube, 3 cube, right? So this is the one. Copy that. Okay, cube. Okay, now we can see the pattern. So A to the K power, any power, we can make that P matrix P, and then diagonal matrix with the K power, and then inverse of matrix P. Then there will be, let me just change that, right? The power. Okay, there will be that. So power. Okay, so there will be we multiply. So we get 2 to the K and 0, and multiply negative 2 to the K, 0, and there is a 3 to the K, the second row has 0, -6 to the k power, right? And then we have 2, 1, -1, -1. So that will be 2 to the k times 2. And minus 3 to the k. Then we multiply this way. So 2 times, -2 times 2 to the k and 2. And minus 6 to k. Hold on 1 second. Yeah. Hold on 1 second. I screw up again, right? Hold on. So let me fix this one. So this will be, we have -2 times -2. So I made a mistake. Oops, I made a mistake here, right? So -2 times 3 to the k power, right? Okay, then we need to fix this one. So everything is good so far. So this one, yeah. So we got this one, right? And we will do this one. So there will be -4 times +2, 3 to the k power, right? Good. Thank you. All right. Now, so we do this one. Oh my gosh. Now this one, right? So we have 2 to the k minus 3 to the k, correct? Okay, now we're doing this one. So -2 to the k, +2 times 3 to the k, correct? Okay. Yes, thank you for confirming in the direct message. Okay, so that is the one. So can you see that? Every time if we have a power, we can easily to make power product of power, right? So that's why we need a diagonalization. So this is the section about. So let us do this. But then this is a lot of work if we don't have eigenvalue, eigenvector. So let me write down definition first. So diagonalize the matrix form is like that. Diagonal matrix. So in general, we have any numbers as diagonally, right? So make a dot, dot, dot. So make more. Okay, rest is 0, 0. So any number. Non-zero. Okay, now definition. So they say that diagonalizable. Diagonalizable. Okay, so we have let a diagonalizable. Okay, let A be matrix n by n, and A is said to be diagonalizable. If there exists an invertible matrix P such that we have inverse of P, A, P, which is diagonal matrix, right? Also, we can express this one. Look, if we have this one, we can multiply P left side, then we get I, right? Now we want to multiply inverse of P here. Okay, then we can express A as the matrix P and diagonal matrix and inverse of A, inverse of P, inverse of P, A. Okay, so we can express that one is like that too. All right. Let us do this one. Theorem. Eigenvectors and diagonal matrices. Okay, A's n by n matrix and diagonal table. If and only if. So let me denote if only if like that, right? Yeah, we're gonna do that. All right. So we're gonna find the P, we're gonna find the D in here. If only if there is invertible matrix P given by P equal to x sub 1, x sub 2, x sub n, so where, look, P is eigenvectors, all right? X sub n are eigenvectors of A, right? How do you find eigenvectors? We need to have eigenvalues, right? So we are using the form lambda I minus A, right? And X to find the eigenvectors, right? Okay, now let me write down if we have invertible matrix P, right? So that means inverse exists, right? Okay, so this is eigenvectors. This is eigenvectors. Okay. All right. So let us do this. We know how to find the eigenvectors last time, right? So we need to find the eigenvalues, and then we are finding eigenvectors by using eigenvalues. Then there will be P, right? If we have a P, then we can find invertible matrix for P, right? Then we can find the diagonal matrix, which is right there. product of matrix P and diagonal matrix, or we can have A, right? That is, we are looking for diagonal matrix, right? So inverse of P and matrix A is given. Then we have a eigenvectors with a matrix as P. Then there's a diagonal matrix. All right. So it's like that, a lot of works. So let me write down steps. So to find the diagonal matrix. Okay, so step 1, find eigenvalues of A. So we are looking at determinant of lambda I minus A equal to 0, right? Okay, so step 2, if we have eigenvalues, we are looking for eigenvectors. So we had earlier x equal to x of 1, x of 2, x of n, right? So I want to make a note here. Eigenvalues. My equal to 0, right? But eigenvectors so like x eigenvector not equal to 0, right? Yeah, cannot be equal to 0. We had it earlier, right? The last lecture we proved, right? Yeah, kind of prove. Okay, so we cannot have eigenvectors cannot be equal to 0. Yeah, thank you, TA, for pointing out. So that will be P. So construct P from the vectors in step 2. There will be P, right? Okay. Now, step 4, we are looking at inverse function of a matrix P and so we have using diagonal matrix of inverse first and A and the matrix P to find the diagonal matrix, right? Okay. All right, let us do this. Okay. So I brought numbers matrix from other textbook because your textbook has a fraction, which is hard to calculate, right? So we have A equal to 0, 0, negative 2, 1, 2, 1, 1, 0, 3. Okay, so we are finding invertible matrix of P and a diagonal matrix this such that inverse of PAP product of, then we get the D, right? Diagonal. Okay, how do we find? So determinant of lambda I minus A equal to 0, right? Okay, so please correct me if I make a mistake. So determinant of lambda and 1 0 0 0 1 0 0 0 1 minus A, which is 0 0 negative 2 1 2 1 1 0 3 equal to 0. Okay, scared. All right, so we have lambda 0 0 0 lambda 0 0 0 lambda minus, we have, okay, when I copy, I copy wrong sometimes, right? So that is more the scary part too, right? So 0, that happened the last time. That's why we have that positive 10. Okay, so we will get lambda, and we get lambda minus 2, we get lambda minus 3, and 0, and that is positive 2, right? And that is positive negative 1, that is negative 1, that is negative 1 0. Is it correct? Excellent. Thank you very much for confirming. All right, so we will have a determinant of that. So 3 by 3 is easy, right? So we can do that. So we will get lambda positive. So we have lambda minus 2 minus 1 0 lambda minus 3 and minus 0. Good. We have 0 plus 2 negative 1 lambda 2 negative 1 0. Excellent. So we have lambda, woo, and lambda minus 2 lambda minus 3 minus 0 and plus the 2 0 minus plus lambda minus 2. Yeah, equal to 0. Okay, small mistake where?
From the left side, minus 0. Oh no, never mind. Yeah, that's my bad. Yeah, you're right. You're right.
Okay, thank you. All right, so we have a lambda. So we multiply. So there will be lambda squared minus 3 lambda minus 2 lambda, which is negative 5 lambda plus 6 and plus, and we will get 2 lambda minus 4 equal to 0. Is okay? Okay, now we distribute. So we will get lambda cubed minus 5 lambda squared plus 6 lambda plus 2 lambda minus 4 equal to 0. Okay, now we have lambda cubed minus 5 lambda squared plus 8 lambda minus 4 equal to 0. 0. Okay, so maybe this is a cube. Good thing we can show you like last time, right? So maybe we can use the decimals to find the one root, right? Okay, TA, can you please give it to me 1? And then we can use a synthetic division. How about that? Because the last time we are using the long division, right?
Yeah, so lambda equals to +1. Right now, I'm
Positive
pretty
1?
sure. Yeah, +1, yes.
Positive 1. So let's see. So from decimals graph. So we have a lambda equal to 1 is the one root. Okay, so we get synthetic division. So we are using just the coefficients. So we have 1. We check the power, right? Descending order. And then -5, +8, and -4. And we always bring down 1. And then the root has the form, which is binomial lambda -1, right? So we can use just 1 there. If we have lambda +1, so we're gonna use -1 as a divisor, right? This is synthetic division. Okay, so we always bring down, so we multiply, what do you get? It's 1. We added them. So we have -4, good. We multiply, we get -4. We add them, we get +4. And we multiply, then we get 0, right? So always the last one is the remainder. Thank you very much. And then next one is a constant and degree 1, right? Degree 2. So there will be, we can express lambda -1. We have a lambda squared minus a 4 lambda plus a 4. Okay, now how do we factor out this one? So we get lambda times lambda 2, right? So minus, right? So we get 0. Okay, so we knew that lambda -1, lambda -2, we talk about the multiplicity, right? So multiplicity of 0 twice, right? Okay, so that is lambda equal to 1, lambda equal to 2, right? Okay, so we have a lambda. We finished that. Now, so we are using this formula to find out eigenvectors, right? So there will be lambda I minus a x equal to 0, right? Okay. Step 2, step 1, eigenvector. Step 2, for eigenvectors. So when we have a lambda equal to 1, right? So for lambda equal to 1. So there will be 1 0 0 0 1 0 0 0 1. I am doing this one. M minus A oops, copy A. Okay, then we make x of 1, x of 2, x of 3 equal to 0 0 0. Okay, so there will be 1 0 positive 2 negative 1 negative 1 negative 1 negative 1 0 negative 2 x of 1 x of 2 x of 3 equal to 0 0 0. Okay, thank you very much. Okay, so let's make a RREF, right? So
Wait, can you go back for a sec, please?
sure.
Okay, that's good.
Okay, so we have 1 0 2 negative 1 negative 1 negative 1 negative 1 0 negative 2, and I skipped that part, right? Anyway, we're gonna come back later, right? Okay, so the TA gives us, okay, very nice, so we can use that. So that's not complete, right? Let me see, oops. Let me see the chat. Oh, it's complete. Okay, let me see. 1 0 2, it's 0 0 1 negative 1 0 0 0 0 0. So TA gives us thank you, Lynn. All right, so we get this is x of 1, x of 2, x of 3. So which one is free? So x of 3 is free, right? So x of 3 is free. So that is, we get x of 1 plus 2x of 3 equal to 0. We have x of 2 minus x of 3 equal to 0. Okay, so x of 3 is free. So we can express x of 3 as 1. So say x of 3 equal to 1. Then x of 2 equal to, it's 1. Yeah. X of 1 equal to negative 2. Is okay? All right. So we get x of 1 negative 2 x of 2 as positive 1 x of 3, which is it's 1, right? Okay, negative 2 1 1. Good. Okay, we do the same process for lambda equal to 2. So for lambda equal to 2, so we have lambda I minus a x equal to 0, that is 2, 1, 0, 0, 0, 1, 0, 0, 1, and minus a. A is this one. Copy. So we have x of 1, x of 2, x of 3 equal to 0, 0, 0. Okay, now let us do that. So I'm gonna do one step, so please correct me. So we will get 2, we will get 0, positive 2, we'll get minus 1, 2, 0, negative 1, negative 1, and 0, and negative 1. Please correct me if I make a mistake. Okay, thank you very much. Didn't message. Okay, so we have x of 1, x of 2, x of 3, and we have 0, 0, 0. Okay, so let's make a skip, and then we make 2, 0, 2, negative 1, 0, negative 1, negative 1, 0, negative 1. We get 0, 0, 0, and TA gives us RREF, which is 1, 0, 1, 0. Thank you very much, Alice. So 0, 0, 0, 0, and 0, 0, 0, 0. Okay, so this will be x of 1, x of 2, x of 3. Which one is free? X of 2 is free. X of 3 is free, right? Okay, so we have x of 1 plus x of 3 equal to 0. Okay, we can say anything. X of 2, what do you want to say? X of 3. X of 3, say 1. Okay, then we get x of 1 equal to negative 1. And we have x of 2 equal to what? What do you want to say? X of 2. Yeah, SNT, yeah, we can make a SNT correct. We can say it earlier. If you want, you can say the S. Here, you can say the T if you want. Okay. All right, so x of 2, what do you want to say as a number? Okay, we say that x of 3 is 1. You can say the 1 if you want. Yeah. Say 1. It's up to you. Yeah. 1 is easier, right?
Oh, it's
Okay.
it's like you can make it whatever you want.
Uh-huh.
Oh, okay.
Because
Cool.
it's a free variable. Yeah, it's a
Oh,
everything.
okay. Okay, that's what it means by okay.
So we have x of 1, x of 2, x of 3. So we get x of 1, which is negative 1, positive 1, positive 1, positive 1, right? Okay, so we done that. Then look, step 3 says say that we construct P, right? So we have construct P from the step 2. So there will be we get let's see. P which is X eigenvectors, right? Correct. So how do we use that, right? So there will be 1 from -2, 1, 1. Oops. And we get -1, 1, 1. Can you use it twice? Or can you change that? What do you want? So we can use, what do you want to say? Say X equal to 3? Oh, hold on 1 second. So we will have this one. We can express this one as S or T, right? So we will have S, then -2, 1, 1, right? Yes. How about this one? So we get, this is, we were using S. So we are using T for this one. Okay, then like addition, we have another one, right? So that is, we get 0, and we get, if we have a 1, then we get 0, right? If we have, well, no, we cannot have that. Hold on 1 second. Okay, so we get -2, 1, 1, that is correct. And then from this one, right? So we want to clear about this one. So since we get -1 and 1, 1, so I want to make that -1 and plus whatever parameter, right? And then we get T 0. Okay, hold on 1 second. -1 and 0 and 0, 1, correct?
Yeah,
And
yeah,
1,
correct.
0, correct? Yes?
0, 1. Yes, correct. Totally
Yes,
correct right now.
correct,
Yeah,
correct,
that's correct.
Yeah. Okay, so we are using -1, 0, 1, 0, 1, 0, right? That is correct?
Yes.
Okay, so basically we got this one here, but since we have 2 eigenvectors, right? So we using this way, right? Yes?
Yes.
Okay, good job. So that is the matrix P construct eigenvectors, right? Okay, now I think I was using some variable too, huh? Okay. So inverse. Oh, how do you find the inverse? So this is a 3 by 3 step 3, find inverse. Okay, so what we do, we can make, oh, really? You meant the identity matrix? Okay, so can we still use them? Row deduction operation. Okay, so he was using, oops. So he was using that. How about that? And this 1 0 0, right? 0 1 0 0 0 1. Okay, so we are, this means we have PI matrix to make I and inverse, right? Okay, do we have one, or we need to get through this one? Yes. So what do you get? So we get 1 0 0 0 1 0 0 0 1. So we have a negative 1 0 negative 1 1 0 2. Ooh, it's so fancy. 1 1 1. Yeah. So inverse will be, it saves us a lot. Negative 1 0 negative 1 1 0 2 1 1 1. Ooh. Okay. Finally. Okay. Look, we have find diagonal matrix, which is inverse and A, inverse of matrix P and A and product of P. So we have this one. And we have A. So A is this one. Copy. This one. Okay, sorry about that. No space. All right, so we do and matrix P eigenvectors. So we have this one. Copy that. Come on. Okay, so we multiply, right? A lot of work. Okay, so let us multiply. Oh my gosh. Ah, he gave us, what a nice. So that is a complete or just a first two? Complete, okay. All right, so, oh my gosh, so nice. So this will be 1 0 0 0 2 0 0, 0, 2. So this is diagonal matrix. All right. Okay. So since we don't have time, I want to finish this one. And second example is about why we cannot make a diagonal matrix, because the eigenvector is 0. So we cannot have eigenvector as 0 vector. So that in that case, we cannot make. I'm gonna write down one more time. So second example. Well, I'm not gonna go over because we don't have a time. So we cannot have I have eigenvector since there is no variable. Okay. All right. So any question? Okay. Thank you for coming. You have a nice evening.